I think we have to start. Other people join us during the conference, I think. First of all, everybody welcome. Thank you very much for your coming to Nazarbayev University. Let me begin with the giving the floor to Professor Adesida, who is the provost of Nazarbayev University. He is, I think, recently will celebrate your 1 year being in Nazarbayev University. Professor Adesida joined us practically 1 year ago. He was a provost of the Urbana-Champaign, University of Urbana-Champaign. He was the dean of the engineering school of the same university. And he also has some relation to the Berkeley labs. So please, the floor is yours.
Thank you. Thank you. Good morning. Good morning. I can hear you. Good morning. Okay. Maybe there's coffee out there to wake everybody up. But thank you very much. As Dr. Baigarin mentioned, I've been here for just about a year, about exactly 10 months. And I arrived from Champaign, Illinois, and everywhere looked the same. Flat, snow, a lot of snow. The only thing I miss is the corn and the soybean. There's no corn around, there's no soybean around, but I understand there's wheat. People ask me, why did you come here? I think bringing international stars to campus for the students to see, to interact with our faculty, and to hopefully help us spread news everywhere that there is a rising university in this part of the world, in Central Asia, that has high ambitions and really want to compete and contribute to the world, to global society in every way possible. And I'm an electrical engineer by profession. I call it poor electrical engineer. I've looked at the titles here. I'm not sure I can understand many. I can read the words, but I don't think I understand the physics. My own profession is in the nano area, more on high-speed electronics. But I'm sure when I look at this, I start looking at what is the difference between philosophy and creation. This is about, in terms of looking at the fundamentals of the creation of the world, of how the world came to be, the galaxy. And I think these are things that we keep being at the edge or the limits of human affairs forever. Essentially forever, because you can never discover everything. Maybe Big Bang, somebody will come with all the theories and actually discover exactly when things happen. But my own vision is that it will be very difficult. But people like Nobel Prize winners and coming Nobel Prize winners will be able to help us solve all these problems. But thank you very much. Please, this is a big university, growing. Please go around. Many of the students are not around yet. Some faculty are around. Please interact with them. See our facilities. They are growing, and we are filling them up as fast as possible. We are hiring. We have over 400 professors from about 50-something different countries on campus. Many of them are on vacation, but they'll soon be back. They'll soon be back to campus. So please, come back. Keep coming back. We have the ECL here, so come and interact with them. And again, hopefully next year, we'll be able to hold another conference, maybe here or in Berkeley. And we'll try to be, wherever it is, we'll be there. And I hope, and I want to make sure that I invite you to the next conference. Thank you very much, and thanks for coming to Kazakhstan. Thank you.
Thank you very much for your very welcome presentation. So, yeah, we in this university, everybody in leadership is very ambitious. Our provost also very ambitious. But I mean, management of the university, of course, very supportive of his ideas, how we can establish fundamental foundation for the developing research in this country, in this city, and in this university. So, thank you again, Adi. Our first speakers, let me give the floor to Professor George Smoot. Few words about their projects. We started 2 years ago as a colleagues, as a friends, to make something here in Nazarbayev University, to understand where is the real future energy. Maybe in universe, maybe nearby us here in Kazakhstan. So, and this is the third year of our project, I think, yeah. So we are very close to opening the laboratory, to install the facility in Nazarbayev University shortly, I think, before the end of this year. We're very close to the starting with some experiments also. So, Professor Smoot, I wish you success for the next 3-4 years being in Nazarbayev University, and I believe this year will be very important for us. We are planning to integrate this project with School of Science and Technology of Nazarbayev University. We talked about this provost, and I think we have a very mutual understanding how this project should move and merge with the Nazarbayev University in future. Professor, your floor is yours.
Thank you. And I mean, thank you to all the participants and the people who came and the few people who are still en route coming here to make this an international conference, and that are going to make it so both we and the students get a good positive experience out of this. It's a mark of Nazarbayev University that I've actually been here longer than the provost. But
from Landau University of Russian Academy of Science. The topic is
about this stage, and actually once more, so it was a stage. It was a stage preceding a standard form of inflationary scenario. Is based on the two main hypotheses, or you may call them ideas, and actually these both ideas are independent ones, and this in particular it follows when in many alternatives to inflation only one of these hypotheses is used, or even none. And so the first hypothesis refers to the background, and the second hypothesis that refers to interpretations. So the first hypothesis is the existence of inflation itself. So, or more exactly, the quasi-parasitic stage, a stage of accelerated, close to exponential expansion of our universe in some period in the past. And then the second hypothesis is about the origin of all homogeneities in the present universe. And so the hypothesis is that they were produced just by exactly this effect, which is actually the complete analog of the effect of creation of electrons and positons in the external electric field. So it's the gravitational creation of particles and field fluctuations for all the vacuum state. It is better to call it adiabatic vacuum or no particle state. It's not possible to introduce this adiabatic vacuum states for all scales, but it's possible to do it for all scales of interest, for all scales capturing all our observable range of scales, and possibly somewhat beyond. By the way, just to illustrate you, as I already said, that if the two hypotheses are independent, in particular speaking about some alternatives to inflation, in particular the so-called theoretic scenario, he does not. Actually, just all observations, actually all interesting predictions, all really quantitative predictions of inflationary models, which can be compared with observational data, are just about the structure of perturbations, and so any outcome of any inflationary models is a prediction about the structure of these perturbations, and it appears that for sufficiently large k, that these quantities in the first the main term is time independent, so it depends only on spatial coordinates, and it has a trace path, and this path just produces all matter inhomogeneities, scalar perturbations, but it's just because it is 5 times 5 matrix. It also has a traceless and transverse path. And what we are interested in, the most interesting quantities which can be directly compared to our observations are just this quantity of power spectrum of this quantity expanded into Fourier harmonics, and the ratio of power of transient perturbations to scalar perturbations. Of course, just because I previously said that the initial hypothesis that this was the origin of all perturbations, so this is really a quantum effect, or even a quantum equalization effect. Of course, strictly speaking, that these quantities are quantum. So in fact, as follows from the derivation to operators, but it appears it happens so, and this is a rather non-trivial fact that just due to expansion of the universe, this operators has very specific structure. They contain powers and powers of this quantity, and this non-commuting quantity appears only it is actually exponentially small, but is actual the value at astronomical at cosmological scales is of the order, say, about E20th order of this quantity. And so if we omit this quantity, and actually just because it depends on time, already when I said here that in the main approximations this quantity is time independent, actually this means that I already omit this quantity, and once this quantity is omitted, it appears that though formally this metric perturbations, strictly speaking, they are quantum even at the present time, they all commute with arbitrary combinations of events, and so that's why it's possible to introduce equivalent, not equal, but equivalent classical stochastic quantities. And then once more, our initial hypothesis that were produced from adiabatic from no particle state and oscillator and quantum oscillator in the main state is Gaussian. That's why it appears that the statistic of this quantities will be Gaussian too. And this is actually confirmed. So once more, okay. And so that's what we actually have from our observations speaking is this map of C and B temperature and isotropy. Of course, just because, as I said, it is strictly speaking, it is quantum, but equivalent description it is a classical stochastic quantity. Okay, and so that's why we expanded into Fourier harmonics, and this is just with multiples. And you see that indeed I'm too equal. So you see in the first approximation the assumption that the primordial spectrum is smooth. It gives us very good agreement with observational data. No, well, of course, I would say up to accuracy in some places of the order of 10%. Indeed, we see here some features, and this shows actually that all idea that we have some smooth inflation and smooth power spectrum is not an absolute statement. It is only a very good approximation up to possible some local features, and that's why still how much time? Okay. So once more, that's why about what I shall speak further is not a final picture. It's a I would say, a good description up to possible local effects of the order of 10% or some of inflation. Okay, and so that's why we also have a similar picture about the mode of polarization, and in particular, a non-trivial prediction of inflation is that though there exist two possible modes of polarization, E mode and B mode, if the prediction is that B mode should be suppressed, at least by one order of magnitude compared to the E mode, and actually this prediction is concerned. We actually measure the E mode and we have only upper limits on the B mode. Okay, and so that's why I would say that the present status of innovation that we have not only theoretical models, we have many numbers, and from these numbers, the most important for us are these two numbers. Two numbers. So the first of them, which was actually mentioned in the previous talk, is the amplitude of this power spectrum, and you see that it is indeed very close to the exactly scale invariant one, the so-called the Heisenberg spectrum, just because this quantity is small. But what is very important that still it's not exactly the Heisenberg, it is the spectrum, and I would say that from the fundamental point of view, the most important achievement of the last CMB experiments, in particular, is the Planck is the measurement of this quantity. And that really, from the theoretical, from the present state of the art, so these quantities are actually two new fundamental logical dimensionless numbers, and from the present state of the art, we cannot explain this quantity. We have to take this quantity only from our observations, but in the most the simplest model, it's possible to predict this quantity, and actually that was done 30 years ago. And then anytime when somebody tells you that he can explain or he predicts some fundamental fundamental quantity, in particular there were many attempts to predict or define structure a constant, the immediate question is in which terms, in which which numbers or for which expressions is this if prediction made. The answer is, omitting some details, but the prediction about this quantity, that this quantity which refers to something which was formed a very long time ago, it actually finally it is related to this quantity that which characterizes, in some sense, it characterizes how large is the present universe, because what stands here is the Hubble constant and the temperature of cosmic microwave background, and you can see by your own eyes that approximately this quantity by models multiplied with quantity is approximately 2, and actually I shall very heavily use this number. Actually, from respect, you may indeed extract much information. Okay, so once more, as I said, in the best model, the simplest models which have the maximal predictive power, they depend only on one parameter, which is actually finally it is related to this number. But in this model, it's possible to predict this number. Okay, and so that's why I would say just because we have not only upper limits, we have actual measurements and at least two fundamental numbers. It's possible, I would say, that the present status of inflation is the transition from either prove it in general and testing some of its simplest models to applying the inflationary power trading to investigate particle physics and super high energies and the actual history of our universe using the real observational data on these two quantities. Okay, and so just to show you an example of direct approach, so we introduce some simple inflationary models and compare them with observational data. So you see that actually, in particular, the best if we look at the use Paul Planck data for temperature and polarization, then indeed, and this is 1 sigma and this is 2 sigma, you see that many models are all already excluded. In particular, I would say that twice squared model is excluded, but still there exists models which just in the center of the region permitted by our observations. Okay, and this is this was what we have in 2015 actually, and this is what we have more recent data. So indeed, as compared to this initial Planck data, we have a much more stringent restrictions. So indeed, 5 squared model is certainly excluded, but the only disadvantage of this figure is that its authors did not show here the model which was shown here, the so-called R-squared model. So it is still sitting here. Okay, and let me just show you this example of the simplest model. And historically, it was the first model. It was the first internally consistent model of inflation, and it was based it was introduced in my paper, in my 1980 paper, and then I followed in some sense I tried to follow the Einstein idea about generalization. So let us try to construct inflation, assuming that it can be described only in the geometrical language. Of course, as we understand now, it's just speaking about Einstein, the theory of relativity. We understand that the idea of the full generalization is not the final one. It's not the absolute one. It's only some very good approximations. And so I would say that in the same should be expected here. But it appears that if we consider this theory, I shall discuss it in my next slide in more detail, then it appears that indeed it contains only one arbitrary parameter, which is fixed using this first number obtained from our observations, this small amplitude of the scalar power spectrum, and then it appears that this mass is of this order. And then what follows is just this prediction, which is once more it's a very good argument with this number. And actually, it's just as I said, what we have from this, that we have upper limit on the quantity R, which is more exactly it is the 0.07% upper limit. So the real prediction is in this model that it should be even one order of magnitude. It's less, but not so much less. So indeed, and this is the effective Lagrangian of these models, and I just write this coefficient with dimensional coefficient using only our observational data, and if you import this value of the measured power spectrum, it appears that indeed it's a constant, and this constant is so large. Okay, and then it just comments that indeed it appears if you now step once more, it's an effective model. It's an effective model, and so if you try to think what is its microscopic origin, it appears that it can equally well can be obtained either as a specific case of fourth order gravity, and the only significant change, what we really obtained from our observation, in contrast to the naive idea that if you have dimensional coefficient here, the naive idea that it should be of the order of unity, where nature tells us that this coefficient is in fact large. And why it is large? Because our observed perturbations are small. Okay, and so, but equally well it can be obtained from just going the opposite way, just trying to introduce some scalar field. In particular, one may try to say that it's a Higgs field, but it's not necessary. But then it appears that one has to introduce this large coupling, and just because in some sense there exists a law of the conservation of the number of small constants, where this constant, this large constant, if it sits in this effective models, it translates to the large number of this constant. Okay, so once more, this the microscopic origin of this effective models can be equally well either still going in this way, trying to make this model purely geometrical, or you may once more you may obtain from okay. And so just let me show you how in this class how to go in the opposite way. Suppose just following all very important tests explained in the previous lecture, you obtain the power spectrum for all scales. Is it possible to reconstruct the required form of this f over r function? And this is the so-called f over r gravity is the simplest is generalization of Einstein gravity, which does not contain ghosts. So it is internally consistent, and these are equations for this theory. Okay, I shall skip here. Formally, I would say it's conformly the ideal to the Einstein theory that the scalar field with some potential, but it's not so much important for my discussion. The important point is that this model is no more complicated than the Einstein gravity to the scalar field, because in that case, it is known that equations can be reduced to one first order equation, and in this case, in my case, it's possible to do the same. Though the stress equation is the fourth order and the zero equation is the third order, it can be reduced to one non-linear first order equation. And another statement is that the analog of the well-known conditions that inflation in the scalar field models occur only in the so-called slow roll regime. The analog of this slow roll regime in F over R gravity, it appears that slow roll inflation occurs when F over R that has the form R square multiplied slowly changing A. Okay, and when it's in particular when it's if we indeed assume this, when the resulting expressions are very simplified. And so once more, the theoretical problem is the following. Suppose you abstain from direct measurements or some other arguments to this function, only the scalar spectrum. Is it possible to reconstruct the function A and the function F? The answer is yes, it's possible, and it is given by this formula. So suppose once more M is here, is log K of the present case. So suppose you know this things, then from this expression you obtain A as a function of actually K, and from this expression you obtain R as a function of K2. So after that you can exclude. So and the only final observation is that, of course, both integrals are indefinite integrals, and so the statement is, so the answer depends on two arbitrary constants of integration, but one of them is not important. It only gives a shift in scale, so it's not important. But second is important, and so the statement is that if you indeed obtain, if you know this quantity from observations, P as a function, power spectrum, scalar spectrum as a function of K, you can reconstruct this model up to one the physical constant of integration. Of course, now what can be done without using any new numbers not yet obtained from observations is assuming that in some sense no new numbers exist. And this corresponds to the assumption that you have first scale-free spectrum during inflation, and this means that P is proportional to log K in some power first, and second, that you also do not assume existence of some new physical scales either at the end of inflation or even after it. In particular, though if indeed it appears that primordial black holes exist and contribute significant part of that factor, then my hypothesis will be incorrect. So this would indeed require existence of some new scale, or from the mathematical point of view, existence of some new dimensionless number. But once more, as far as it is approved, and this new dimensionless number is not measured in contrast to ns-1, so let me work with a minimal number of assumptions, and then it appears that if you, once more, if you introduce no new dimensionless functions, then you just obtain the only possibilities r plus r squared model, and in particular, this is just seen from this example. In particular, if we assume that the power spectrum is log k squared, then indeed we obtain this expression, and from this expression, if we want in particular to have Einstein gravity at low r, the only possibility, as I said, in this case is not possible at all, and in this case it's only possible if we say that this arbitrary constant is have, and this is just r plus r squared model. Okay, I shall stop here, and let me show only my conclusions. That really, so once more, of course, if you introduce additional hypotheses, then you may make some many new models, and not specifically inflationary models. You can make new models of elementary particles, physics, new models of irregularity. But once more, if you want to use only those numbers which have been already measured, then the remaining possibility is not large. In particular, so speaking about specifically in inflation, I would say that we have not really quantitative observational evidence for these small quantities, actual measurement of this quantity and the upper limit on this quantity. We have confirmation of typical inflationary predictions. Typical means for this very wide class of models that this quantity is small, and although this quantity, once more, this quantity shows how large is the present universe, and the R does not exceed this quantities, and this quantity is 0.3. And when these predictions, which are generic to almost slow rolling inflationary scenarios, are confirmed. And once more, typical consequences, if we do not assume some additional small parameters, first, that there was period in the past of our universe when it was as curved as this quantity, and then there exists some particle or quasi-particle, scalar particle, or quasi-particle with this characteristicness. But, as I said, if we use more information following from our observations, that ns is not simply of the order of this quantity, but it is approximately 2 divided by this quantity, and r is 0.07, no, I would say it's 4 times, actually, much less than this quantity. Then we have what remains is a rather narrow class of inflationary models, which may be equally well realized either using a minimally coupled scalar fields, or in particular in F over gravity. Okay, and then, as I said, that in both cases, I cannot talk about Einstein gravity, but equally well, as I said, we can reconstruct from observational power spectrum, smooth power spectrum, we can reconstruct up to one arbitrary constant of integration. And what is important is you actually, as follows actually from this result, approximately in 1/2 of this models remaining viable, this value is sufficiently large, and it's remarkable that it's possible to measure this quantity. But once more, if we assume that we don't have any new scales, not only at the end of inflation, but also after it, then once more we have a definite prediction for this quantity. Okay? Thank you.
Thank you very much. First of all, thank you very much for your time. So having a wider scale, like a universe, so yeah, both speakers in time, absolutely. So, and I invite everybody to participate in the discussion with questions.
So you made the point early on that your theory is wonderfully predictive on the main inflationary parameters, but you also have this advantage that in the second aspect where the quantum creation comes in, the scalaron decay and the reheating is predicted as well. Are there any non-Gaussian correlations that are coming out of the theory that could be tested?
So, I was speaking about non-Gaussianity.
Exactly.
So the prediction is that non-Gaussianity is very small. So once more, if we use this minimal theory, which has only one parameter, the statement is that this theory does not predict either a significant amount of primordial black holes first, and this predicts a very small level of non-Gaussianity. So once more, of course, it can be well falsified, and indeed it may just in the case if you say remember the case of say the particle is that physics or the initial hypothesis by Wolfgang Pauli was about the existence of Ivan neutrino. Now we know that there exists at least fragment of event. So indeed, it may well appear that the nature is not so simple, and that we have to introduce new. I always prefer to speak about the number of arbitrary parameters in the model, which have to be taken from our observations. So once more, if in particular observations will show that there exists some number, say exceeding one, regarding non-Gaussianity first, or if we actually measure the amplitude, not upper limit, but we actually measure this amplitude of the scalar power spectrum at some sufficiently large scale, at some small scales, which is for all the measured amount of primordial black holes, then indeed these models it will be not sufficient, and this means, but I would like to emphasize that this would require some new physics. So it will be not simply inflation, it will be inflation with some new physics, or speaking more concretely, all these simplest models in fact assume the existence of one effective scalar field for quasi-particles, and we know, and actually we know all already. In particular, it was just investigated in some of our joint papers with Professor Schmutz, that if we want to obtain some breaking of local breaking of the slow long condition, the most natural physical justification for this is to introduce some, say, a second particle which is typically massive, but it becomes massless at some very short period of time, and it is just, and this results in the breaking of the slow flow approximation. So I would say that indeed this model, this simple models may be well falsified in the future, but this will occur due to some new physics.
Thank you. Alexey Alexandrovich, we discuss some modified general relativity, Einsteinian generalization, to describe the early stage of the universe, so inflation. Is this model appropriate to describe the whole history of the universe? It's pretend to describe to be the universe model, or it's just a part of some general theory of gravity, and we need to construct to do some additional construction and so on.
Well, once more, as follows from this form, and in fact, it's the simplest form. So this is the Einstein term, and this is the statement is that any correction which produce non-Einsteinian behavior should not be such that the second derivative of the functions should be known as zero. And of course, the simplest function which second derivative is known as zero is a quadratic function. But just from this result that m is so large, it follows that this model, where this term is not important at later times in particular. So it's the other question: is it possible to use some other model of this class, some other model to represent some alternative to the present dark energy? The answer, though indeed there were a large number of such attempts, but I would say that the answer is that it's possible, but that the resulting first you have to introduce by hand another dimensionless constant, which is much less and just of the order of the present, and so of the present logical constant. So still the small number remains unexplained first, and second, even from the mathematical point, it appears that the functions, the possible functions which are not excluded by observational data, I would say they are rather anesthetic. anesthetics. So though I would say formally still this possibility exists to construct an alternative to the cosmological constant, speaking about a description of the present dark energy. I would say that I would from aesthetic reasons I'm rather skeptical about it, and as we all know, existence observations still do not show any statistically significant deviation of the present dark energy from an exact Einstein cosmological constant.
Actually, my question was very similar to the previous question, which has already been yourself. Sorry? Can you introduce yourself? My name is Pawan Kumar. My question was very similar to the previous question, which has been largely answered, which is to say that the term R-square term that you introduced in the FR gravity plays very little role at later time. But I just have a follow-up, very brief question, and that is, yes, I do understand that it plays a very small role at later time, but the question is quantitative. At a later time, if you look at clusters of galaxies, the dynamics, gravitational lensing, then this model has, one can use this model to make calculations. And I wonder whether you or somebody else has done that for this model to make sure that everything is consistent.
Indeed, as I said, it was done, but actually, once more, it was calculated, it was all considered, but once more, just because R now is so small, that this term is unimportant, and this is a more physical statement was contained in my statement here, that actually the existence of the storm results, as I said, in the existence of this particle. So the question is, what happens with these particles? The answer is that all these particles are actually unstable, and they decay after the end of inflation. And it's once more the elegance of this model that one does not need to introduce a special mechanism for the decay. The answer is that one has to use essentially the same mechanism as was used to produce perturbation. So the same effect of creation of particles in the external gravitational field works twice in these models. During inflation, it helps us to produce at very large scales perturbations, but after inflation, it results in the in terms of quantum theory, it results in the decay of these particles. So all of these massive particles actually decayed a long time ago.
Yes, last question, please. Yeah, a little bit.
I see this. If we take into account the additional 10R squared, how it will change the perturbations of dark matter, how it will change the perturbations of baryonic matter, and how it is possible, it will change the scales of galaxies and so on. What can you tell
Once
about?
more, as I said, at R much less than m squared, and this occurs simply after the end of inflation. This term can be neglected. That's all. So speaking about effective Newtonian potential, it produces the Yukawa force, but its radius is only 5 times larger than the Planck scale. So it is exponentially damped. at this small skills.
Now, rush of time, please. Okay. Thank you, both speakers, for very outstanding introduction to our conference. Now it's coffee break.